Yeah, welcome to numerical methods. And we had a section on the acceptance rejection method, yeah, which was part of our section on generating drawings of other distribution in the chapter of random number generation. And yeah, we are done actually, let's say, with random number generation and also with acceptance rejection. But I would like to add a small part today how we get from exception rejection sampling to the weighted Monte-Carlo method. And this is maybe a nice motivation. So let's maybe just recall acceptance rejections sampling was here this lemma. So actually you generate drawings of a tuple of random variables u and y. Yeah? So here these two guys in orange and blue. And then you have a certain criteria, which is here below. So is your sampling of U smaller than the density F applied to Y divided by C times the density G applied to Y, yeah, where G is the density associated with the sequence Yj. So Y is G distributed. And F is now the density of the sequence that you would like to generate. So that is here my sequence X. Yeah? So when this criteria is fulfilled, you accept the point, and this gives you a sample point X. Otherwise, you reject the point. So with this criteria, you filter some points out of the blue sequence to obtain here the green sequence. We had this little nice example, for example, here with the normal distribution, how we can generate a normal distributed sequence by filtering a double exponential distributed sequence. So here the blue line in this picture is the distribution function of the double exponential. Okay, and then you have this acceptance and rejection criteria. So you sample another point, and if the point is in this region, you accept the sampled point, and if the U is in this region, then you reject the point. So actually, you sample a tuple, so a sample from the two dimensions to get a one-dimensional vector. So what happens if we use this method and generate a sequence that we will use in the calculation of a Monte-Carlo integral? Okay, so we started with the question on how to generate a sequence with a given distribution. So we have here the acceptance rejection method, and this method is a little bit inefficient, yeah, when the acceptance rate is low, so when we throw away a lot of points. But now consider the case when your application of this sequence is Monte-Carlo integration, and then we discover that maybe we do not need to throw away the points. So my application is I would like to calculate here the expectation of a function h, yeah, applied to my random variable x, so the f distributed random variable x. So my Monte-Carlo integral is take the sum over all function evaluations h of xi. Xi's are now the drawings, yeah, and average the result. Yeah, and now let's assume that xi is generated with acceptance rejection sampling. So what does this mean? This means that I throw away certain elements from a sequence yj. So I generate a sequence yj, and now I check the criteria f applied to yj divided by c times g applied to yj. Compare that to your uniform distributed u, yeah, your sample uj. If uj is below that bound, keep the point. If it is above that bound, reject the point. So in a Monte-Carlo integration, I take a sum, and instead of rejecting the point, I could just add a 0 to the sum. So I can represent my acceptance rejection by an indicator function, which in my sum just multiplies the result either with 1 or 0. 1 if I accept the point, I sum the point, 0 if I reject the point. So instead of saying that I apply h to the sequence xi, I could also just say I apply h to the sequence y, j, but certain yj's are wiped out in the sum. So this is just the part that now goes here in this sum. Yeah, what about the number of points that we sample? Well, we sample as many points as we require to get n, little n, different xi's. So the n here is associated with the number of xi's that we would like to have in our summation. For the yj in the acceptance rejection method, so here in this picture, maybe you need many more points until you have generated n different xi's. So we need to accept n points. This means that there is some m, so how many points y, j I have to sample, some m, and the sum over now these indicators where we accept the point, this should be equal to the n. So now this little bit complicated expression could go now here into the n that is in front there. And you see, I can write now my Monte-Carlo integral, so average the function evaluation h applied to the sequence xi. I could write it when xi is generated with acceptance rejection in a complicated way, apply h directly to the sequence yi, but set some of the summons to 0 when you reject the point. How many points do you sum? Okay, we sum m different points here. And we divide by the number of points that have been accepted, which is by construction here my n. So I divide here by the sum over the indicator functions. You could also add a 1 divided by m in front, here and here. Okay, that doesn't change a lot. Okay, and now your Monte-Carlo integral looks like that. Okay, apply the function h to your y, multiply with the indicator function if that point is accepted, and divide by the average of those indicators. Okay, so that's all the same thing. That's just if you do Monte-Carlo integral with a sequence that has been generated by acceptance rejection. But now consider the following. What happens if this yj here is now the same for different j's? What happens is that sometimes you have a 0 here, sometimes you have a 1 here. So if you go back to the picture that we had in the script or here this experiment, so sampling the y is actually sampling this point here. If the y is fixed, you sample the u, and sometimes you accept the point, sometimes you reject the point. So I have now an indicator function that lies along that line here. So instead of just throwing away some points, multiply with 0, or keeping some points, multiply with 1, I could just multiply with the relative frequency of these points. So we could just decide here what is the proportion between that part and that part. And instead of multiplying with the indicator, we keep the point, but we multiply with this weight. So we could here replace that part maybe with a weight that represents how many points are accepted. And maybe then here, I'm just summing over all these weights. So in the sum, we multiply with 0 or 1, depending on the sampled y and uj. So that's just what I mentioned. And if you consider the y being fixed, instead now of setting the valuation to 0 for some use, we could maybe improve it and just consider accounting for the relative frequency by using some weight. Yeah, indeed, if you look here at this part, just look at one of the two sums you observe there. This is a Monte-Carlo integral of this function here. And this function is a function in two dimensions, in u for your acceptance and in y for the sampled point. So this sum here, apply h to y, and then multiply with the indicator. This is the Monte-Carlo approximation of a two-dimensional integral. Well, we have an integral over the u. So u is a uniform one, so comes from 0, 1. Density is just 1 du. So an integral over the u. And we have an integral over the y's. Okay, the y's live, say, on the whole domain. The density g decides now about the domain g dy. Nice thing is that the integral over the u part, this can be calculated analytically. So from the two-dimensional integral, I can make a one-dimensional integral. I can integrate the u part, and this means that here we can calculate this weight depending on the fixed y. Okay, so just move the h of y, so applying the function in front, and then you see you have h of y multiplied with integrate the u part, which is just integrate now this indicator function, integrate your acceptance criteria. So this guy, let's call it r, depends on y, for the fixed y. This guy, we have calculated it before. So integrating this indicator function from 0, 1, okay, this is just the integral 1 from 0 to f of y divided by c times g of y. So integrating this indicator function just gives me 1 divided by c f of y g of c times g of y. So if you plug this in here, so you now have for this part the analytic solution 1 divided by c f of y divided by c g of y. Then you see that what is left here is a one-dimensional integral. It's just the integral h of y times this part here times g of y dy. So this is, I integrate the function h of y times r of y. So this is a Monte-Carlo integral of this function here that depends on the sampled random variable y. So you see, instead of having here on the left-hand side the indicator function and approximate the two-dimensional integral, I can also have here on the right-hand side just the weight where we had previously the indicator function, and that approximates this one-dimensional integral. Of course, the two sums are not the same, because what had happened is that I have moved to the integral, so I have actually m went to infinity, and then I have integrated over the u. But the two sums approximate the same value. And this here looks a lot more efficient, since we use all random numbers that we have generated. it does not happen that we throw away a few random numbers. So if you look back to this picture here, actually, if you do Monte Carlo in 2 dimensions with the pseudo random number generator, actually you would sample different points here, yeah, in the 2-dimensional domain, and some points are now thrown away. Yeah, this guy here is thrown away, this guy here is thrown away, and others are kept. Yeah. But now we keep all the points and just multiply with the weight. Okay, so instead of having here my Monte Carlo integral, apply h to your xi, where xi is generated using acceptance rejection. So that means I apply h to yj and have a certain indicator function here. I could also just use all the points. So I apply h to y. Okay, now I move to an index I, yi, and I just multiply now with this weight r here. And maybe, yeah, intuitively in front, we sum not over the indicators, we sum over the weights. Okay, this is all a little bit heuristic. I will prove now that the result will also converge to the same value as the Monte Carlo integral here on the left-hand side. Our R is f divided by c times g of y. So you see that you can actually cancel the c parameter, the c constant, which is here with a 1 divided inside and here with a 1 divided inside. So if I now set w of y to be c times r of y, so that means w is just the ratio of the two densities. So w is f of y divided by g of y. Then I could also, instead of 9, just write here in number 10, apply the function h to y, multiply with w, also applied to y, and divide by the average of these weights, w. Same, this Monte Carlo integral, yeah, actually these two, the ratio of these two Monte Carlo integrals also converges to expectation h of x. Okay, so that's easily seen. First, the thing that is in front converges to 1 because the average of these weights, w, applied to y, this is just the expectation of w of y. So this is just my integral. So this is just my integral. Okay, what was w? W is density f divided by g. Okay, I apply to y, so that means I integrate with respect to g dy. So you see the g cancels, and integrating the density f gives you just a 1. So you see that this guy in front here, this converges to 1. Okay, so this part here is just the Monte Carlo integral approximating the expectation of h of y times w of y. So what we are left with is this part here, and this is approximating expectation of x, okay, y, okay, you see this is approximating expectation of apply the function h to your random variable y, apply the weight w to your random variable y. So expectation of that is like integrating with respect to g dy. Okay, we integrate h times w, plug in w, w is f divided by g. So your w is just f divided by g. So you see that the g cancels and we are left with the f. So we just have integrate h with respect to the density f of y dy. And now I just rename, yeah, so this is just renaming here. This is not a special step, this is just rename y to x, okay, because the integral doesn't care if I write a y or an x. So you see what you are effectively doing is you integrate h with respect to the density f dx, that is, you calculate the expectation of h applied to x. Yeah, we have a nice alternative Monte Carlo approximation. We can take a sequence, a random number sequence y. Y has a different distribution. And we multiply all our results with the weight w. W being f divided by g, the ratio of the two densities. Okay, and then we average this term, and this is a Monte Carlo approximation of expectation h of x. Yeah? So here we have a Monte Carlo approximation of expectation h of x, but the i's are samples of y. So that would happen if we use acceptance rejection in a Monte Carlo integral and are a bit clever to not throw away the points, but to just account for their relative frequency. And this thing that you see here is called weighted Monte Carlo. So you have a Monte Carlo approximation with a certain weight, and this trick can be used in different ways to improve the Monte Carlo integral. So let's give a definition to this. Yeah, I need a certain condition that allows me to do this. Yeah, and you see there is a ratio here in this weight. So the weight is f divided by g. Yeah. So I should not divide by 0, but okay, sometimes it doesn't matter if g is 0. So the condition that I need is if g is 0, g applied to y is 0, then f applied to y should also be 0. So what does this mean? This means that if the point is impossible as an outcome in the G density, then it should be impossible in the F density. Yeah, clearly you would like to approximate your expectation H applied to X. So you sample actually points of X, but now you use this weighted Monte Carlo by sampling Y. And if there are certain regions that are impossible in the Y sequence, they should be impossible in the X sequence, because otherwise you are missing a certain part. Okay, so let the condition hold that g of y equals 0 implies f of y equals 0. And then we call this expression 1 divided by n, sum h of yi w of yi, yeah, where yi's are now drawings of the random variable y. We call this the weighted Monte Carlo approximation of the expectation of h of x. The weight is called likelihood ratio because it adjusts for the likelihood of the point. Okay, so that was a little bridge, yeah, now from acceptance rejection to weighted Monte Carlo. Small remark, you also saw that here in this little application, yeah, of the normal distribution sampled from a double exponential and a uniform. You can interpret the acceptance rejection method either now as a two-dimensional integral. So that's here the two dimensions you see here. So you sample your v, which gives you the point y, and you sample then the u, which decides on the acceptance or rejection. Or you can interpret it as a one-dimensional integral by integrating the vertical axis here along the vertical axis. So by integrating over u, and you just have a one-dimensional integral. Okay, so you see on the left-hand side, I have the two-dimensional integral with your uniform and your y. Yeah? This here is your acceptance rejection criteria. So you have the expectation of h of y conditional to the acceptance rejection criteria. So this is this indicator function. Okay. And this is a two-dimensional integral. Okay. And we can integrate this acceptance rejection criteria. We can integrate this part, the du part, we can integrate it out, and we arrive at a one-dimensional integral, only the v part, which gives me the y. We are inversion of the distribution function. So this here will be the y remains. Okay, so actually that concludes in the script the section on random number generation. Sometimes I have had references, so here are the references that were mentioned in the script.